Welcome to my lab, my first lab for 2212, the charge tapes lab, by me. So the purpose of this lab was to observe the excess charge on a piece of tape that we get by ripping it off another piece of tape, and we want to compare that to a computational model of tape. In the end, our group found that the piece of tape had an excess charge of negative 1.5 times 10 to the negative 8th coulombs, or 9.339% of the 10th electrons, for a ratio of 4.29 times 10 to the 7th atoms of tape per excess electron. The fundamental principles we used here for our lab were Newton's second law, F equals ma, and Coulomb's law. That should be an F there. F equals kq squared over r squared. We use Newton's second law to calculate the force of gravity on this top piece of tape that's causing it to fall. We said that if we want to float the piece of tape with this other piece of tape, those two forces have to be equal. So we find the force pushing up, which is equal to the force pushing down. And from that we can backtrack, because we know k, because that's a constant, we know r squared observationally. We backtrack to find our q. So our initial system is this top piece of tape, and our surroundings are the bottom piece of tape and the force of gravity from the Earth. There you can take a look at my initial conditions. So here's a video of our lab.
Okay, shit, okay. That's good. I'm gonna put this shit right here.
Yeah, I can.
Well, yeah, there you go. As we can see, when we pull the piece of tape up closer to the other piece of tape, instead of like falling out, it actually started floating in the air up, which is from the force of the electrons repelling each other. So calculating our forces, here we have our force of gravity in the negative y-hat direction. We say that that electrical force is equal to that in the positive y-hat direction. That's what causes it to float. Again, we do the algebra we mentioned 2 slides ago. We find that the charge on the tape is 1.5 times 10 to the negative 8th coulombs. Some simple division gives us that we have 9.33 times 10 to the 10th electrons on that piece of tape, and for a ratio of 4.3 times 10 to the 7th atoms of tape per electron, per excess electron, I guess, in that piece of tape. Here's the computational model I built for this. You can take a look at it for yourself if you want to. But like, yeah, it works. So here are our computational results. As you can see, the charge per piece of tape we calculated computationally was negative 1.6 times 10 to the negative 8th, and then number of electrons, 1 times 10 to the 11th, ratio 4 times 10 to the 7th, all very close. I think the number of electrons we found initially was 9.33 times 10 to the 10th observationally, so, within one order of magnitude, and we said 4.92 times 10 to the times 10 to the 7th, 4.29 times 10 to the 7th as a ratio observationally. Computationally, we observed 4 times 10 to the 7th. So again, all very, very close figures. So we made some assumptions. First, we said that air resistance is negligible when the piece of tape is going up into the air. We said there's no air resistance pushing it back down. So the tape is a point charge. Obviously, it's not. It's a strip. And we said most importantly, we said there was no loss of electrons to insulators, which there definitely was, because I'm holding the piece of tape in my hands. Some of those electrons are going to go to my hands. And again, another one of the errors could have been an uneven polarization of the tape, which really I have no control over. And then for our discussion, what if questions, if the charges of the protons and electrons were flipped, nothing would change, because they would still be like charges, and they would still repel each other, and you'd still get that floating effect. And then for why it's important not to handle the tape too much, again, as I mentioned earlier, when you handle the tape, you get electrons into your hands from the tape, and that reduces the excess charge you're going to observe on that piece of tape, which is going to reduce the accuracy of your lab. So that's my lab. Thank you.